So, hello. My goal in this presentation is to provide insights into how UV-visible spectroscopy can be used to characterize gold nanoparticles, focusing particularly on gold nanorods, although many of the points discussed here can be applied to other gold nanoparticle morphologies. So, gold nanorods exhibit two localized surface plasmon resonance modes. These are associated with the excitation of a plasmon resonance by light that is polarized parallel to either the transverse or the longitudinal axis of the nanorod. The key parameter deciding the positions of these two modes is the aspect ratio of the particle. The transverse mode is typically around 520 nanometers, although it blue shifts slightly with increasing aspect ratio. The longitudinal mode redshifts dramatically with increasing aspect ratio, allowing the peak absorbance to be tuned from the green to the infrared. Smaller nanorods have high absorption and low scattering, whereas larger particles' optical response is dominated by scattering. Plasmonic resonance below 620 nanometers is heavily damped by inherent electronic properties of gold. So this damping originates from interband transitions. This can be seen in the density states diagram for gold, where the electrons located in the D band, highlighted in pink here, can be promoted to unfilled states in the SP band by photons with an energy above 2 eV. Above this energy, the quality factor for the plasmon resonance increases by nearly a factor of 10 between 520 nanometers and 650 nanometers. The important point, however, is that this effect is proportional to the number of electrons and hence the quality of metallic gold that's present. So hence, we can effectively decompose a gold nanorod spectrum into three parts: the transverse and longitudinal resonances and absorbance due to interband transitions, which are highlighted in the three colors here. And we can note that at 400 nanometers, the dominant effect is absorbance due to interband transitions. We can exploit this because it means that the absorbance of 400 nanometers is directly proportional to the concentration of metallic gold in solution. Compared with the concentration of gold obtained using atomic absorbance spectroscopy, it shows a strongly linear correlation with a gradient of approximately 0.405 millimolar. At this point, it should be noted that if the particle is large enough, scattering becomes important. This approximation becomes significantly less accurate. However, for most gold nanoparticles, this remains an effective route of measuring the concentration of gold in solution. So what else can we learn from the spectrum of gold nanoparticles? There's a large amount of qualitative information that can be extracted from the spectrum. The plasmon band position could be used to estimate the average aspect ratio of the nanorods. The full width at half maximum and shape of the longitudinal localized surface plasmon resonance band is indicative of the size dispersion. And absorbance of 400 nanometers, as previously stated, could be used to estimate the concentration of gold in solution. The ratio of the longitudinal to transverse localized surface plasmon resonance peaks and the shoulder on the transverse band can be used to signal the presence of byproducts from the synthesis. So finally on this point, the UV-vis spectrum is a crucial piece of evidence for understanding the nature of a sample. The spectrum probes all particles in a suspension, whereas an TEM image is a sample of the nanorods. TEM images can be misleading. For instance, these two TEM images are different areas of the same grid. A good TEM image alone is not enough to indicate a high shape yield, as impurities can be hidden in different areas of the grid. So now I want to talk about monitoring gold nanoparticle syntheses using UV-vis. Typically, gold nanoparticle syntheses use chloroauric acid as the gold precursor, which has a spectrum that looks something like this. In a gold nanorod synthesis, typically CTAB is then added, which results in a change of color as a gold-3 bromide complex is formed. Then a mild reducing agent is added, such as ascorbic acid, which results in a clear solution with very little absorbance. Because of this, the presence of unreduced gold can easily be measured by UV-vis. Typically, a 1.5 molar excess of ascorbic acid is required to reduce all gold-3 to gold-1. This point of the reaction can be used as a baseline for monitoring the nanoparticle growth. Then, either a strong reducing agent, such as sodium borohydride, or gold seeds are added, and the solution slowly changes color over the course of several minutes to hours. So we can then perform this measurement as a kinetic measurement over the entire synthesis. We can directly monitor the kinetics of the reaction, and because we know the conversion factor of the absorbance of 400 nanometers to the concentration of gold 0 in solution, we convert this to a reaction rate from the derivative of this curve. This is extremely powerful because we can, for instance, compare the kinetics in the presence of additives, such as oleate, which dramatically increases the time scale over which reactions occur. Finally, we can infer what is happening to the distribution of gold nanorods in terms of their morphology. We can monitor the full width half maximum of the longitudinal mode during the gold nanorod growth and see that the peak continuously narrows throughout the synthesis, indicating that the monodispersity in the aspect ratio is continuously increasing throughout the synthesis. By tracking the peak position of the longitudinal mode, we can also observe some unusual behaviors. The peak aspect ratio increases continuously throughout the reaction until suddenly it reverses and begins to decrease, suggesting that gold nanorods change from a regime where there is preferential growth on the tips to a regime where there is preferential growth on the sides. The other thing that is visible is that the gold nanorods are present in solution from the earliest spectra that we collect, where plasmonic peaks are visible, suggesting that the morphology is formed very early in the synthesis. In conclusion, I hope that you can see that UV-vis spectroscopy is an extremely powerful tool for studying the properties of plasmonic gold nanoparticles, allowing a large amount of important information to be extracted from their shape, purity, and concentration, and then growth kinetics. It is an important complement to the data that can already be provided by electron microscopy.